Okay, so I've got a question. I'm going to be using the Wilcoxon signed rank test, and I have got some data about average CO2 emissions between 1990 and 2000 in the table, and I'm going to be testing to see whether there was any change. Okay, so the way I'm going to be looking at that is when I come to do this test statistic, we're going to be subtracting these to find out about changes. So I can either talk about differences in my hypotheses, or I can just stick with what it says in the question and talk about changes. So the null hypothesis is something unexciting, it's something definite, and that is, in this case, going to be that there is no change in CO2 emissions. So there we go. In this kind of test, we can always have a similar H0. Now for H1, we have to read the wording carefully. So we are looking for any change in average emission levels. So therefore, we don't need an increase. We don't need a decrease in particular. We're just looking for any change. So that's the wording that I need to use in my alternate hypothesis. So that's going to be that there is some kind of a change in CO2 emissions between these dates, and that is going to make this a two-tailed test. So there we go with our hypotheses, okay? And now we've got to go on and actually do the test. So in part 2, we've actually got to start doing our calculations. So we're going to need to do some ranking, but before we can do ranking, we need to get the things we need to rank. And in this case, we have got, for the Wilcoxon test, we are going to be looking at the differences in each of our matched pairs, okay? All right, this is matched pairs data because I have 9, it looks like, columns in my table. I don't have 18 different nations involved. I just have 9 nations involved, and I have 2 readings for each nation. So that makes this matched pairs data. That's why I can use a Wilcoxon matched pairs test. Okay, so I'm going to do my subtractions. Now I'm allowed to do this in either order. So 8.1 and 8.2, I'm going to do the top line, take away the bottom line. So I'm going to get a difference. So in my first row here, I'm going to work out the difference. And in each case, I'm going to do the top one minus the bottom one. So my first difference is going to be minus 0.1. And then I'm going to do 10.2, take away 9.9, and get 0.3. And I'm going to continue filling in the row that way. And what's really crucial here is that some of these differences are positive and some are negative. It's a signed rank test, so we need to be able to distinguish between both. However, the next thing we need to do is to rank these differences in order of size. So, this one here is not a small difference. That's a very large difference. The smallest differences are these and this one, and in fact they're equal. Now for this particular exercise, this second row in the table, you can regard this as optional, okay? But you may find it helpful just for temporarily to look at the differences just in terms of their size. So to just throw away all the minus signs and record all the differences as positive values just for the purposes of ranking them. So if I filled all of these in, I've now got positive numbers, and now I can see that these two are equal smallest, so they both get the rank of 1. Oh, except they can't both have the rank of 1. I've got to use up ranks 1 and 2. So my tied ranks must be 1.5 and 1.5, which is the average of the ranks I need to use, 1 and 2. And now I've got 3 tied ranks. I've got 0.3, 0.3, 0.3. I've used up ranks 1 and 2. So my next set of ranks is 3, 4, and 5. Okay, the average of those 3 values is just 4. So all of these have to be taken as having a rank of 4. And then my next rank, so that's 3, 4, and 5. So the next available rank is 6. So that goes to the next smallest value, which is this one. And then my next smallest one is this one, 7, and this one, 8, and this one, 9. Okay? Now, that is completely ignoring signs, just looking at the signs of them. So now I need to go back and put the signs back in. So that's what the fourth row is for. Okay, so I could just write a minus on this to go with a 0.5, or I could write out minus 0.5. I'm going to do the second one. What's vital here is that we end up with a link of ranks. That was a minus 4. I'll end up with a list of ranks which were based on ranking the sizes of the difference, ignoring the sign temporarily, but have now got the signs attached to them again. Okay, and to work out my test statistic, okay, I just need to do the totals of the ranks. So the total of the let's call it R plus. The total of the positive ranks is going to be the positive numbers in this list. So not this one, it's negative. 4 plus 6 plus 1.5 plus 9 plus 4 plus 7. Okay, and they all add up to 31.5. If I'm right. And then for the negative ranks, I add up the negative values. Okay, now I could count them as being negative, but what I want in the end is the absolute total. So this is a minus 1.5. I'm just going to do 1.5 plus 4 plus 8. The point of the plus and the minus is to separate out these two totals. So I've got one total that applies to the positive ones and one that applies to the negative ones. But when I actually use this answer for the total of the negative ranks, I turn it back into a positive number. And that's because the critical values here, okay, you can see that everything is positive. Even though, it doesn't say at the top, but this table that you've got in your formula book, okay, this one here refers specifically to the low end of the table. So that means of these two values here, I always work with the smaller one. Okay, this test is two-tailed, so that's perfectly legitimate. If either of these results falls in the relevant tail, then that means I have a significant result. Okay, on a one-tail test, okay, if I'm expecting CO2 levels to be falling, that means that I would be expecting the differences to be a higher value minus a lower value. So here's CO2 falling. I'd be expecting positive answers. So if I'm expecting CO2 to fall, then I'd expect the sum of the positive ranks, I'd expect the positive differences to beat the negative differences, which is what they seem to do here, which is why I've got a sum of positive ranks bigger than the sum of negative ranks. So I can look at these and see which way round the data seems to be pointing, and for a one-tail test, that would matter, because if I've got significant evidence the wrong way round, then that is not significant in a one-tailed test. I'm alright here because it's two-tailed. So, as always, we take the smaller of these two numbers, okay, and then we draw our diagram. So this is my test statistic. My test statistic is 13.5. My critical value, okay, well now I have to use the table, and the thing that I need for the table, at the top of this column, is I need a value for n. Now, n is just the number of matched pairs. So going back to my table, I think we commented that there were 9 countries here. We counted them. Okay. Oh, look, it even tells me in the question there are 9 countries. So n is 9. And I've got a significance level. I've got 5% significance level. Oh, and I'm doing a two-tailed test. So, using all of that information, my n is going to be 9. So I'm going to be on this row here. Okay. And I am doing a two-tailed test at the 5% significance level. So I need this column. So my critical value here is 5. Okay, so my critical value, n, it was 9. Okay, it was a 5% significance level, and it was two-tailed. So that's all worth setting up before you use the table. We looked that up in the table, and we got the critical value is 5. So show me that nicely and clearly. And now I do my comparison. So my numbers are 13.5, and what am I doing? 13.5 and 5, and clearly 13.5 is greater than 5. Now what does that mean? Okay, I didn't do my diagram, did I? Okay, so which tail am I looking at? Okay, I always choose the smaller of these numbers, because although it doesn't say it on this table here, this is always the low tail critical values. Okay, look, we've got noughts here. That's never going to be a high tail critical value, is it? These numbers might look big, but these are for massive values of n, where when you do it, you find the sum of the ranks is just a huge number normally, and these are actually at the very low end of the spectrum. So the table always gives me a low value. Okay, so this bit here, the big unshaded bit, that's my not significant bit. This is my significant bit. Okay, so 13.5 is greater than 5. So which side am I at? I'm in this bit. I'm in the not significant bit. You can put 13.5 on your diagram if you like. Okay, so I have got a not significant result, and if it's not significant, that means I'm going to be accepting H0. Okay. Alright, so I've got a decision, but now I've got to put that decision in context. Now here, you've got to be really careful with your wording. This is accepting H0. Whenever we accept H0, we're in the not significant bit. We haven't got evidence of anything. We needed to be in this shaded bit to say we had evidence in favour of H1. So you never get evidence that H0 is true. And if you look at some of the model solutions, these are wrongly worded in this case, fairly consistently. Okay, what we want for any situation where we're accepting H0, we need to start by saying there is no evidence, and then we can look at what we've got no evidence of. Okay, so in order to reject H0, I'd need evidence for H1, which is that there's some change. Well, we've got no evidence of that, so therefore we can write down there is no evidence of any change in CO2 levels between the dates. There we go. Now we're kind of done, but actually when we're interpreting this, when we're stating our results in statistics, we should be very clear about the significance level we use, which is 5%. So I can put in my 5% here, 5% level, and I can start with my conclusion. At the 5% level, there is no evidence of any change. Or I could put that in after no evidence, alright? But it's crucial that I have the words no evidence there whenever I'm accepting H0. And now this is a fully correct solution.